That's not a cosine cube. It's cosine over sine cosine squared. So that's a 1 over sine cosine. So what is that? Cosecant? Secant? Alright, that might be right, or it might be wrong. Hold on. Embarrassing math teacher moment. Yeah, 1 over sine cosine. Yep, 1 over secant cosecant. Okay. Beautiful. Hopefully you understand that. This entire process has a name. It is called logarithmic differentiation. And the key idea of logarithmic differentiation is that you have a function that you would like to differentiate that doesn't have any logarithms in it, but you take the log of both sides in order to break up the function into tiny little pieces which are easy to differentiate, and then you can take the derivative of ln y easily by doing this sort of roundabout manner, and then you get this. Okay, awesome. Good. I'm going to erase this and then do some more. All right. So we're like getting to the point where you can almost differentiate everything. There's just a couple more things to go. And here is one function which has already come up as a function that we don't know the derivative of, and that is the derivative of 2 to the x. And you will recall from a previous video or a previous class that when we tried to do this on the same day that we came up with the derivative of e to the x, we tried to differentiate this function, and we got that this is the limit as h goes to 0 of 2 to the x plus h minus 2 to the x all over h. We weren't sure how to do this, but by rewriting this as 2 to the x, 2 to the h, and factoring out the 2 to the x, we end up with 2 to the x times the limit as h goes to 0 of 2 to the h minus 1 over h. And then we had this limit, which we had no idea how to compute, and we couldn't really figure out a way to do it. But we did learn that the derivative, we learned from this, assuming that this limit exists, and it does, we learned that the derivative of 2 to the x must be 2 to the x times some constant. In other words, the 2 to the x function increases at a rate proportional to itself. And what is this mysterious constant? We can get some more information out of this by graphing the function and thinking about it. So the 2 to the x function kind of looks like this, and this limit can be interpreted as a derivative. It is the derivative of the function at 0. In other words, the derivative of 2 to the x is 2 to the x times a constant, which is in fact the slope of the tangent line to the curve at the magic point. And if our function is e to the x, then that slope is 1, and so we get a beautiful formula. And if it's something other than e to the x, like 2 to the x, we get an ugly number. So all right, what is that ugly number? Well, it turns out that the best way to do this is just to, well, there are many ways to do this, but one way to do this is to just use logarithmic differentiation. So you have y equals 2 to the x, and you want to differentiate this. Well, like, I have this feeling from Algebra 2 and pre-calculus that when I need to figure out some crap and my variable is like hiding up here, then somehow logarithms are like appropriate. And so you should already feel like, yeah, logs to the rescue. I call this, there's a princess trapped in a high tower. So if there's a princess trapped in a high tower, you rescue the princess with logarithms. So let's do that right now. Rescue the princess. Take the natural log of both sides. This is one way to do this. And so suddenly, now I use the log rule that ln of 2 to the x is x times ln 2. And now suddenly this is just like simple. The exponents are gone, and now everything's nice and easy. Keeping in mind all the while that natural log of 2 is just a number. It's about 0.7. So since this is just a number, well, I know exactly how to do this now, right? What is the derivative of ln y? Just like from a few minutes ago, well, again, I guess if we want to be nice about this, we should just be explicit that what we are doing in the next step is to differentiate both sides with respect to x. What is the derivative of ln y with respect to x? Derivative of ln of something, 1 over something, back inside for the derivative of the something. What is the derivative of x ln 2? Well, since ln 2 is just a number, like 5 or something, this is just asking like, what's the derivative of 5x? And the answer is ln 2. So, what is dy dx? What is the derivative of that function? It's y times ln 2. In other words, 2 to the x times ln 2. Alright, so there we have it. It turns out that the slope of this line is just ln 2. And again, this is why the exponential function e to the x is like the real function that we love and care about. Every other exponential function increases at a rate with just this annoying excess factor. Okay, so I think this is great, and in fact, what we have really derived, there was nothing special about 2, what we've really derived is a more general rule that the derivative of a to the x is a to the x times ln of a. Alright, this is a way to do this. In every other previous year, I did this a different way, which I always liked better, but the students hated it. You might like it, so we'll talk about that now. Another way to do this is just to be very fancy with your log rules and to just think of 2 to the x as e to the ln of 2 to the x. If you just know, since 2 to the x is, since e and natural log are inverse functions, then e to the ln of anything just is that thing. So if that's the case, well then I can subsequently write this as, I can pop down the x using the log rule. So this is really e to the x times ln 2. Well, what is the derivative of e to the x ln 2? Well, I know how to do that. It's a chain rule situation. This is basically asking me for the derivative of e to the something. So the derivative of e to the something is e to the something back inside for the derivative of the something. And what is the derivative of x ln 2? It's ln 2. And now, you just put everything back where it came from, right? Now pop the x back up. So this is e to the ln of 2 to the x times ln 2. And e to the ln of 2 to the x is 2 to the x times ln 2. Alright, it is the exact same thing. If you analyze the logical structure of these two derivations, you will find that they are really identical. It's just a matter of, do you like to sort of do these manipulations with e and ln and inverse functions and log rules, or do you want to just kind of write it out in a linear fashion, temporarily naming the function y? There are pros and cons of both approaches. But anyway, you should be comfortable with these derivations and also just know it. Alright, this is amazing. What's left? Now I can differentiate basically any exponential function. How about logarithmic functions of other bases? If you are unfortunately dealing with some terrible person who wants you to differentiate if you're forced to deal with some disgusting function like log base 3 of x, well, how can I differentiate that? All right, there are two ways. Again, there's a way which is a little bit like tedious but possibly easier depending on your personality. So let's do that first. I never used to do it this way, but I think we're going to do it this way now. Let me make sure I don't screw this up also. So I think what I'm going to do is use the definition of the logarithm. If y equals log base 3 of x, like what does that even mean? y is the number that I raised 3 to get x. So this just means that 3 to the y, well actually, if you want to get technical about it, what I'm really doing is I'm 3-upping both sides. So if y equals log base 3 of x, then 3 to the y must be 3 to the log base 3 of x. Well, by the definition of logarithm, 3 to the log base 3 of anything just is that thing. So 3 to the y is x. Okay? So, cool. Now, I still have this exponent that I don't feel like dealing with. So what I'm now going to do is I'm going to take the natural log of both sides, rescue the princess. So we take ln of 3 to the y equals ln x. So what I get is y ln 3 equals ln x. And now differentiate both sides with respect to x. So take the derivative of both sides of this equation with respect to x. Well, the derivative of ln 3, so okay, what's the derivative of y with respect to x? It's just dy dx and times ln 3. It's constants, don't do anything. And what's the derivative of ln x? 1 over x. Ta-da! Final answer, dy dx is 1 over ln 3 times 1 over x. Ta-da! Alright, it's actually pretty nice and pretty easy, and again, once you do it a couple times, there's your formula, and you can easily memorize it. If you want to be a little bit cooler about it, you can use the so-called change of base formula. And the change of base formula for logarithms says that if I want to take the log base a of b, then that's the log base c of b over the log base c of a. Alright, if you are like good with logarithms and you know the change of base formula and you're comfortable with it, then you can just apply that to this problem. So if I want to differentiate log base 3 of x, I recognize that log base 3 is really like an illusion, and the only real log function is the natural log function. And the change of base formula is precisely the formula which allows me to move back and forth between logs of many bases. So really, that tells me, please differentiate ln x over ln 3. Well, that doesn't scare me because I can think of this as 1 over ln 3 times ln x. 1 over ln 3 is just a number. So this is really like saying, all right, what's the derivative of this number times ln x? And the answer is, it's this number times 1 over x. So we get the same thing in both ways. If you are an astute observer, you notice that essentially I basically am just re-deriving the change of base formula over here, right? If I stop at this step, taking the thing inside the red brackets, and I divide by ln 3, well, what have I just done? I've just reproved the change of base formula. So, all right. So whether you want to use the change of base formula, or you want to just do it out from scratch every time, it's pretty easy to come up with this formula. And again, you'll just memorize it because you use it so often. All right. Dude, I can do everything now. Derivatives of all the trig functions, composite functions, exponential functions, logarithmic functions. It's pretty amazing. All right. What is left? What is left? Well, there are more things. There are more functions. One such function is a crazy function. It's a function which looks kind of awesome, and you may have wondered, yo, Ms. Rose, how come we never saw this function before? And this function is y equals x to the x. Well, pretty impressive, or pretty scary, I guess. What is the x to the x function? It is a, well, I don't know. Okay, one reason why we have never dealt with this function before is because it's just too weird. It's actually, without calculus, it's too difficult to really be able to say much of anything about this function. All right, so of course, what I'd like to do is differentiate it. How? Okay, warning. So I'm going to write over here on this side of the board, I'm going to write a bunch of wrong things that are not true. All right, this function, y equals x to the x, is not an exponential function. Not an exponential function. And it is also not a power function. Okay, so there's a couple of just like really bad things that you should never ever do. If I am trying to differentiate x to the x, you cannot just treat it like it's some kind of exponential. Like, oh, I know, I just learned how to differentiate 2 to the x. It's like, I don't even know what to write. It's like x to the x times ln x. Okay, no. It is also not a power function. So you would be crazy if you tried to differentiate this and we were just like, hey, don't I just like bring down the x or something? That's just, again, that's just no. So wrong and bad. And hopefully you're laughing, wondering who could possibly do such a terrible thing. But I'm a teacher and I've seen terrible things like this happen before. So one day someone will be just like tired and not paying attention and not thinking, and they'll try to differentiate 2 to the x and they'll treat it like a power function. X times 2 to the x minus 1 or something like that. So bad. So much no. So much no. Alright, how can I do this? Well, it's pretty obvious. There's only one thing I can possibly do. Rescue the princess. So take the natural log of both sides, and when I do that, I have ln y equals x ln x. Now suddenly it becomes possible to differentiate this, because I know how to differentiate products. So what is the derivative of ln y? Well, again, same thing. We now differentiate both sides with respect to x. And if we differentiate with respect to x, we get derivative of ln y, 1 over y, back inside dy dx. Oh, pause and do the problem yourself. Let's make sure you get the same thing I got. Differentiating the right-hand side with respect to x over the first times the second plus the first times the derivative of the second. And so what we get is that dy dx is multiply both sides by y, which is just x to the x, times x plus 1. Awesome! This is another example of logarithmic differentiation. And logarithmic differentiation is, again, it's this process by which we start with a problem that has nothing to do with logarithms, but take the natural log of both sides to enable us to more easily differentiate. Unlike the other problem, in which I could have done it without logarithmic differentiation, but that would have been annoying, here logarithmic differentiation was obligatory. So there's no way of getting around it. In the other problem, it was optional to take the log of both sides. Here, it's necessary. All right, and this is part of a more general process which will enable us really, this is really a process which essentially enables you to differentiate anything of the form f to the g, assuming you know the derivative of f and the derivative of g. So let's maybe just do one more example. And let's see, if you were in period 3, this is exactly where we got to on Friday. And so period 3, you should be joining the class right now with another example. So I don't know, just make up one. How about like cosine x to the x cubed. So take a minute and differentiate that right now. exponentiation is right associative, so that means that. Just wondering. So, differential along both sides. Apply log rules. And now differentiate implicitly. Derivative of ln y, 1 over y, x. Now I have to use a product rule first. And second plus first times derivative of ln cosine is 1 over cosine back inside for the derivative of the cosine. Alright, so dy dx is just y, in other words, the original function, times this gross thing. Let's see. Can I factor anything out? You can factor out an x squared. So that's 3 ln cosine x. Or if you want to be kind of cool about it, you can pop up the 3. Cool people do that. So this is ln cosine cubed x plus or minus x tan x. Cha. La 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 la. La la la. Is that right? I think so. Okay, awesome. So we now can differentiate all functions of that form. All right. What else? So now period 3 and 8 should be watching. We're going to do something else. And something else is this process of differentiating so-called implicitly can be used to derive formulas for the handful of remaining functions that I don't yet know how to differentiate. And if you recall from last week, or possibly from the video, I used this process to come up with the formula for the derivative of e to the x when I knew the formula for the derivative of ln x. And this process is generalizable, what it really does is it enables us to take the derivative of any inverse function. Assuming I know the derivative of the function, it enables me to take the derivative of the inverse. Okay, so now, unfortunately, you will all must print out a 6-page document from the internet. Sounds terrible, but there are worse things that can happen to you in your life. And so, if you were in period 9, you got this handout on Tuesday. But if you were not in period 9, please find this packet that says Derivatives of Inverse Trig Functions. And it is a 6-page document. And what we're going to do now, in detailed fashion, is come up with formulas for the derivatives of all the inverse trig functions. Okay, let's go. And this packet is actually really nice because this is going to be in the Unit 2 folder, I guess, because this packet actually helps you review all the inverse trig functions because they're all really, really important. And if you've noticed, it seems to be the math teachers are obsessing over them. That is because we use them so often, and they're pretty tricky. So we're taking it all the way over again from scratch. And I first ask you on the top right-hand corner, top left-hand corner of your paper, there is a spot for you to graph tan x. So this is like your last chance to freaking learn your inverse trig functions. If you've been just avoiding them, hoping that they would go away. This is now your final chance. All right, what does tan look like? So please, everyone, graph tan, follow along, stay ahead of me as usual. Tan looks like this. All right. Uh-oh, tan is not one-to-one. Since tan is not one-to-one, when it comes to constructing its inverse, I must restrict the domain. And we have chosen, there was a convention at some point, and everyone decided, hey, let's take the interval from negative pi over 2 to pi over 2. All right, so now we can make the sketch of arctan. What does the arctan function look like? If you're a good student, you just know this already, and so you're feeling like, man, how can anyone in this class not possibly just know what the graph of arctan looks like? Haven't we done this a million times? We have. What does it look like? Well, it's the inverse of the tan function. So there's a thing at 0, 0. At pi over 4, tan is 1. So at 1, arctan will be pi over 4. At negative pi over 4, it's negative 1. So at negative 1, arctan will be negative pi over 4. When I'm a little bit less than pi over 2, tan goes to infinity. So as I go to infinity, arctan goes to a little bit less than pi over 2. And as I go a little bit more than negative pi over 2, I go to negative infinity. So as arctan goes to negative infinity, or as x goes to negative infinity, arctan goes to a little bit more than negative pi over 2. Beautiful, brilliant graph of arctan. A couple things to notice. Tan has a slope of 1 here. Why do we know that's true? That's just true, okay? You could do a limit argument, or you could just know that the derivative of tan is secant squared. So what is secant squared? 0. Secant squared 0 is 1. So since that line has a slope of 1, and the inverse function is just a reflection of that line across y equals x, then I'm pretty sure that the slope of this line is also 1. All right, keeping that in mind, I'm kind of just doing this whole thing for you, which is really terrible because this works really well as an in-class exercise, unfortunately, but so be it. Use that graph. Here are the directions now. On the bottom left-hand corner of your paper is a spot for you to sketch what you think the derivative of arctan should be. So using your curve sketching, derivative sketching skills, please do that. Make a guess for the graph of arctan on the bottom left-hand corner of your paper. I'll wait. Yeah. And the way to do this is just to kind of like move a pencil along the graph of arctan and see what you think the slope is. So if x is a huge negative number, what's the slope of the arctan graph? Should be some tiny, tiny positive number. And now the number is going to be getting bigger, the number is going to be getting bigger, the number is going to be getting bigger, but the steepest the arctan function ever is at 0, where it has a slope of 1. So if this is 1, then I guess what this function must look like is it's really close to 0. At some point it gets a little bit bigger. And by the time I get to 0, the derivative is 1, the slope is 1. And now the slope starts getting smaller again, but it's always positive, it stays positive. Okay, so now the slope's getting smaller, and this is going to be a positive number forever. Alright, so this is my, just like it's laid out on your paper, this is my guess. This is my guess for the derivative of arctan. Alright, that the derivative should look like that. Alright, now that we are like feeling like pumped, and we know everything there is to know about the arctan function, including its domain, range, where it comes from, what it means. Now I think we're ready to differentiate it. So how? Well, we're going to do it in a roundabout manner. I want to differentiate this function, but like I already know what the derivative of tan is, so I feel like I can use that somehow, right? And in fact, there's only one thing I know about the arctan function, which is that by definition, if y equals arctan x, well, then x equals tan y. So take the tan of both sides, if you will. And that's pretty much works, as long as we, yeah. That's fine. Okay, so basically in this one brilliant move, I reduce a problem involving arctans to a problem involving tans. And now you probably just see exactly what to do. I already know how to differentiate tan. My goal, once I said that y is arctanx, my goal was to find dy dx. If you look back at your notes, this is exactly analogous to what we did to coming up with the derivative of e to the x. Alright, so how do we do it? What is the derivative of tan of y? Okay, sorry, so going a little slower. What I do is differentiate both sides with respect to x. The derivative with respect to x of tan y, well, the derivative of tan of something is secant squared something back inside for the derivative of the something. Equals the derivative with respect to x of x, it's just 1. So using the formula for the derivative of tan, I've now basically solved this problem in like one step. dy dx, or two or three steps. dy dx is just 1 over secant squared y, or cosine squared y. Alright, but I don't want to leave it like that, because y is just like that's not what I want. I want to know what the derivative is with respect to x. Okay, so what is dy dx? It's really like, this is really like shorthand for cosine squared of arctan x. Alright, so I'm basically done, but alright, I don't want to leave it as cosine squared arctan because that's awkward. So really now what I have to do is like do some pre-calculus. So now it's time to do some pre-calc. And you know, there's a whole day in pre-calc B and also in pre-calc C where we talked about how to simplify things with the form cosine squared arctan. And what you do is you make a picture. So we make a picture of arctan x. And what I know about arctan x is that it is always between negative pi over 2 and pi over 2. And it depends on whether the input is positive or negative. When x is positive, arctan will be between 0 and pi over 2 in the first quadrant. And when x is negative, arctan will be between negative pi over 2 and 0 in the fourth quadrant. So we're going to consider both of these cases separately. There's the x is negative case and the x is positive case. So to make a picture of arctan, if x is positive, we just agreed that arctan lives in quadrant 1. So my angle is going to be a first quadrant angle. And if x is negative, we agreed that arctan x, which we're calling y, lives in quadrant 4. Now all I have to do is label the sides of these triangles in such a way that I have